Good morning, everyone. As you're joining, we'll give everybody a moment to sign on. If you've just joined us, we're giving everybody a moment to get here, so just hang tight. We'll be with you in a moment. All right, it's 11:01. Let's get started. Hello, everyone. Thanks for joining us. Welcome to the latest installment of Mazzetti's Bending the Climate Curve Learning Series. I'm Christina Vernon Sanborn, the Sustainability Practice Leader here at Mazzetti, and I'm going to serve as the moderator for today's panel. Are you aware that MRIs consume more than twice the energy of CT scanners and 10 times that of X-rays? Today, we'll explore groundbreaking research on MRI energy consumption and discover practical strategies for energy savings in medical imaging equipment. Before we get started, a bit of housekeeping. Today's event qualifies for one AIA CEU. If you didn't provide your AIA number when registering, please send it to info@mazzetti.com. We will hold questions until after today's speakers have made their presentations, but you can submit your questions at any time via the Q&A function of the webinar. Today's session is being recorded. Now I'd like to introduce our panel. Jacqueline Tompkins is a mechanical engineer at Mazzetti and has been working in the healthcare industry designing mechanical and plumbing systems since 2018. In 2021, she joined the research team for the UCSF MRI energy consumption study and the medical imaging equipment energy and heat gain study with ASHRAE. She's been working with hospital partners, industry leaders, and manufacturer partners to help bend the climate curve in our healthcare spaces. Omkar Gatpande is a research engineer in the Building Technologies and Science Center at the National Renewable Energy Laboratory, or NREL. He has completed his graduate and undergraduate studies in electrical engineering. At NREL, his research focuses electrification and electrical distribution systems in buildings, grid-supported load flexibility studies, and evaluating emerging technologies in field study projects. He's also a member of the Better Building Alliance's plug and process loads team. And before NREL, Omkar worked as a senior electrical engineer at ABB and as a solutions development engineer at Honeywell in their buildings team. Next is Dr. Andrew Hernandez. He's an assistant professor of radiology at UC Davis Health. He's a diagnostic, clinical, and research medical physicist with an expertise in breast X-ray imaging, cone beam computed tomography, or CT, and computed tomography. Dr. Hernandez has a special interest in the development of imaging systems, the quantification of radiation dose, and the evaluation of imaging performance utilizing state-of-the-art metrics. He's also the director of radiology sustainability and is committed to minimizing the environmental impact of radiology with a specific focus on improving the energy efficiency of medical imaging equipment. And last, Gail Lee has 30 years experience in healthcare, environmental health and safety in public, nonprofit, and private industries, currently serving as the sustainability director at the University of California, San Francisco Health Center since 2010. Gail provides thoughtful leadership, creativity, and lends an experienced perspective on sustainability, including greenhouse gas emissions, energy efficiency, and toxics and waste reduction at UCSF and at UCSF Health. Gail's particular interest lies in helping healthcare institutions known for their 24/7 operations, energy use, and waste-generating activities reduce their environmental impact. With that, I'll turn it over to our panel.
Right. Hi, everyone. I'll give the overview of our presentation today. And so the first question is really, what is our motivation? Why are we monitoring medical imaging equipment and MRIs in particular? So we'll go over an MRI introduction with basics, operational modes and its typical energy usage, our MRI metering journey, data analysis review, operational strategies as a result of the study and the future of MIEs. Next slide. So UCSF was thinking about ways to identify energy efficiencies across the health system. And as you know, healthcare contributes about 8.5% of US total carbon emissions. The UC system-wide, of the 10 campuses, and we have 5 health systems, we have targeted reducing our carbon emissions by 90% from 2019 levels by 2045. This is a very lofty goal. We're exploring as many ideas as possible. In 2018, we started thinking about reducing energy and carbon emissions from our hospitals. And we realized that perhaps medical imaging equipment was likely the most energy intensive equipment, although we didn't know how much energy they actually used. And around that same time, we started to see ads from MRI manufacturing companies offering more energy efficient models. So I reached out to them, very excited to hear about this, to compare how much more energy efficient were they than our conventional MRIs, but we just could not get the data. So then we decided, well, let's meter it ourselves and determine those numbers. And so in 2021, we realized at that time, US had collectively over 12,600 MRIs. UCSF alone has 27 MRIs, and that's double that of our CT and CT PET scanners. So we started to explore how we could actually do the metering, and we received a $60,000 UC grant to fund this energy study and compare conventional with those that are claiming to be energy efficient. But soon we found out that even UCSF and then UC-wide, who had 75 MRIs, we didn't have enough of these new MRIs to meter and compare against the conventional. So we reached out to the Healthcare Climate Council, which consisted of 18 of the largest health systems in the country, to see if they would be interested in participating. And we also realized we wanted a consultant to help us with our scanning protocols and perform the metering ourselves. And so we reached out to Massetti. So here's our timeline. We started in 2018. We got the grant award in 2019, and then COVID hit in 2020. So at that point, none of the hospitals were allowing anyone outside the hospital system to come onto their premises. So we actually were kind of a dead stop. But we at that time, we continued to work on the protocol and determining, what the metering process would be, what kind of equipment we would use. And that was a very helpful time for us to really narrow down that process. Well, we still had to wait until June 2020 until we can begin metering again. But then it took us 2 more years to finish collecting all their metering due to multiple logistic issues and travel and just scheduling the time. But finally, we completed all of our data collection and data analysis. So we'll hear more about that from Jacqueline. Next slide. So at this point, at the end, we had completely metered 18 MRIs across 4 different hospital systems. We did 12 that were 3 Tesla and 5 that were 1.5 Tesla. 6 of the MRIs literature had actually had energy efficiency claims. So we had 6 of the energy efficiency claiming MRIs, and then the rest were all conventional. So we think we had a good number, 1/3. So we'll talk more about the results, but in this entire project, we had a lot of partners. We worked with Massetti for the data analysis, UC Davis Health And then UC Health System. Also UC Green Radiology Group, which actually started during this time because we kind of garnered a lot of interest in, what can we do around even beyond MRIs. We reached out to Healthcare Climate Council and Lawrence Berkeley Laboratory, and also US EPA. And I had talked with them early on when we first started this, and they had told me that they have been trying to get energy data from the MRI manufacturers for quite some time and had not been able to achieve the data. So they're very excited to hear that we're starting to collect this data. So we definitely want to share it with them, because the idea would be that we would get an Energy Star rating for MRIs. And then lastly, the National Renewable Energy Laboratory was also very interested in this. So all the data that we collected, we'll be sharing with all of those interested parties to ensure that we make that information as useful as possible. Next slide. So again, why medical imaging equipment and why MRIs? We know that for typical hospitals, the energy used for medical imaging equipment is about 5% of the total hospital energy use. And they do consume more energy than most of the other medical imaging equipment. And then, so we've been working with Energy Star to help develop specifications for additional new medical imaging. So we turn it over to Andrew to talk more about the technical issues.
Thank you, Gail. For understanding different energy use for MRI, it's important to categorize the different operation modes. So those broadly can be classified into productive and non-productive time. The productive time could be the scan modes where the individual pulse sequence are actively being acquired. Before I go into the other different types of modes, there's currently no industry-wide definitions, and these names could differ from organizations to manufacturer to the people who are speaking with. There are some of the names which could be similar, but their description could be slightly different based on the background. So these definitions or these details come from one of the papers which was written by the presenters today, with Andrew leading this paper. In this, we tried to have a little bit more details into different non-productive operation modes, because the differences in machine functionality was important to separate to understand how does the energy use differ in those different modes, like prepared to scan, idle mode, low power mode, off mode, and power save mode. Next slide, please. And again, now to measure energy, there could be two types of energy for typical MRIs or MIEs. They're classified for electrical measurements of the electrical power and energy, and thermal measurements. So for measuring electrical power and energy, a typical circuit level meters could be used, where we can calculate the active power or what is the consumption of the energy consumption of that MIE, which will be billed by the utility. Typically, this is calculated as voltage times current times power factor. And then in this, many times, because MRI is always operational, we cannot connect those all those connections for measuring the power. So sometimes we just install the current sensors to measure the current, and then assume some voltage and power factor to at least get an idea how the power could be differing. This may not be used for billing, but can understand the power use. And as everyone knows, you cannot control what you cannot measure. So at least installing to get the load profile of these meters or these machines is important. And on thermal side, there could be some where a chilled water is used to cool down a part of the MRIs. A BTU meter with temperature sensors and flow meters can be installed to understand what is the heat draw from the MRIs. Next slide, please. So from this, on one of the papers that is under publication, we tried to plot the active power versus the time. And in this, we can see different modes of an MRI machine classified based on some of the definitions that we have mentioned before. And as expected, the scan mode is the highest energy consuming portion of it. And different power modes still use energy, but at a different rate. So it's very important to know which mode the MRI is operating at to reduce its energy use and its carbon footprint. Next slide, please. So for a typical connection for an electrical meter to the system, it's connected to an input to the system, but a lot of the MRIs may have more than one input connections. So in order to measure all the power consumed, multiple power sources have to be metered. So the picture on the right shows a typical power distribution box and temporary meters that were connected to it. So temporary meters are something which are used for a short-term or spot measurements for estimating power and energy. These are not ideal for long-term use, where a permanent meter should be used. But installing permanent meters could require pulling permits, or it may take a long time in case of installing if the unit is already operational. So it's important if a new machine has been installed. Installing these meters in advance helps a whole lot in cost and time to install these meters. Next slide, please. So for a typical MRI study, we found out that following personnel are important for the metering study, starting with electricians who install, operate, and configure the meters. And then second most important could be the IT support, who could do the network configuration and get the meter data to your building management system or an energy management system to review that data. Just installing the meters doesn't help anyone if the data has not been processed or looked upon. And secondly, and next, facilities personnel or energy manager is required to access the electrical rooms to know where everything is connected and what is in metered, and for any other general questions. On the medical side, the technologists are essential to operate the scanner for measurements if a temporary meter is installed for doing spot measurements, and also for long-term use, radiologists or medical physicists or clinical engineering are required to understand the potential impacts of the scanner modes and protocols of the testing results. So this may help in understanding the energy side and the medical physics side of that energy use. Next slide, please. So typically we install a few meters at UC Davis Health. Over here, what we connected the voltage sensing, which requires physical wire connections. At UC Davis, we could not connect this because MRI was already operational, but this will be required in case you need to do complete energy analysis. But we did install current sensors, which are non-contact and can be installed when when system is energized. Typically, then we require meters to set up, communication to be networked, and set up for other measurement parameters. Another important thing to understand is the time scale for the meters. If an energy analysis has to be done, a time scales of minute to hour can be useful, but any dynamics have to be studied. The time scale could be a lot shorter in seconds. And similarly, because having a higher temporal resolution is always better, but then it could lead to some other problems like communication or bandwidth issues or storage running out. So a good balance have to be decided when the metering study starts between what the timescale should be. And another point to note out is that there are some MRI systems like standalone MRIs on trailers that may have some other systems that are connected to your MRI main panel, like a chiller, RTU, battery, UPS. So make sure to install additional meters there too to understand what's the MIE's energy use versus other auxiliary loads in the system. Next slide, please. For the setup at the UC Davis Health, as I said, we metered three MRI machines. Two of them were 3 Tesla and one of them was 1.5 Tesla. And we connected non-contact split core current transformers to measure its load. And we used analog data logger to record the current at a time scale of 1 second. And we also tested out a low Tesla resistive magnet, which connects to a typical NEMA 5 120 volt plug. So we used a plug load monitor to measure its energy use. Next slide, please. So on this slide, we have presented some results that we got from spot measurements of one of the 3 Tesla machines. So we found out that the 3 Tesla machine entered the low power mode only after 48% of the exams based on the power and scanner log data. And the time to enter the low power mode was on average 15 minutes. So we did 4 different tests and we tried to measure the ready to scan mode and the off mode power consumption by that machine. Next slide, please. And in this study, then we tried to estimate what if the 3 Tesla machine enters the low power mode after 10 minutes instead of 15 minutes. And what we found out that by just doing this, the scanner could enter low power mode after 81% of the exams. And on those exams, we could save on average 1.56 kilowatt hours of electricity. And then nationally, if we extrapolate this could mean 6.6 megawatt hours of saving for the MRIs. And then if we assume some tradition or some numbers, the national annual saving can be in terms of gigawatt hours. Next slide. Now I hand it over to Andrew.
Thanks, Omkar, and thanks, Christina, for the introduction. So, I think it would be a little bit unfair for us to really just focus on the energy consumption or kind of the cons associated with MRI without first really talking about the immense diagnostic power of this specific modality. So shown here is a diffusion MRI fiber tractography image. And this essentially shows a trajectory of neural tracks where those colors are actually the direction of travel. And so, for example, for neurosurgeons, this is quickly becoming an invaluable tool for planning of their neurosurgery. Next slide. Another very interesting example is functional MRI. So in functional MRI, we're able to localize, for example, areas of the brain that are used during tasks that utilize working memory. So really amazing ability here to be able to visualize these different parts of the brain. Next slide. Okay, so, I think discussing the energy characteristics of MRI scanners, it's very difficult to do that without first talking about really the basic principles. So this is by no means going to be a physics lecture, but really just a quick snapshot to hopefully bring to light some of these specific principles that drive some of the energy characteristics. So the human body is composed of about 10 to the 27 hydrogen atoms. And these are really what are used, are fundamental particles really that are used to create MRI images. And so as we'll talk about in the next slide, MRIs usually use superconducting magnets. And these magnets create a strong magnetic field, what we call B naught. And what it does is it allows for a net magnetic moment of the hydrogen atoms. In other words, it allows for those hydrogen atoms to be able to spin in a particular direction. That's kind of what we're showing in that diagram here. And they spin at a specific frequency that's really proportional to that strong magnetic field. And so when these hydrogen atoms are essentially aligned or they have some net magnetization, we also have what's called gradient coils. And what the gradient coils allow for us to do is they allow for us to slightly distort the magnetic field in a predictable manner. And so the key here is it's predictable manner. So essentially at every point in space, we're able to define the frequency of the hydrogen atoms, which is very useful for essentially spatially encoding the MR signal. And then lastly, we have radio frequency coils. And so there's both transmit and receive coils. The transmit coils allow for us to really preferentially excite hydrogen atoms at a specific location because we know what their their frequency or the precessional frequency is because of the gradient field and the magnetization. And so these essentially excite those hydrogen atoms, and then when they return to equilibrium, they actually emit their own RF pulses. And so we have detection or receive coils that allow for us to detect that transition. So those are both excitation and relaxation, and this is all from radio frequency. And so basically these principles are fundamental for producing MR images, and they really enable radiologists to be able to differentiate different tissue types. However, each of these specific principles requires a significant amount of energy to be able to provide the diagnostic quality expected of MR images. Next slide. And so really the first one that's important to talk about is the magnet. And so the magnet is really the heart of the MRI scanner. It's a permanent magnet sitting within the bore of the MRI scanner. And so these high magnetic fields, they really require superconducting magnets. And superconductivity is essentially a characteristic of certain metals that requires that they're maintained at a really low temperature. And so to be able to maintain this at a super low temperature, of course, requires a lot of energy. And so that's really the fundamental reason why MRIs are always on. Once they're installed, essentially, they're always consuming really some DC amount of energy. And we'll see there are some techniques that have been employed by vendors to really reduce this energy consumption. And we'll talk about that in some subsequent slides. Next. So essentially conventional MRI systems in the past really just use superconducting magnets. Those are always on. But sometimes really these conventional MRI systems are inconvenient and not accessible, particularly for patients, for example, in the ICU that are on ventilators. But really time is critical for these patients. And so to address this, low field systems, such as the one shown in the images here, have emerged as a valuable alternative really for specific clinical scenarios. And so these utilize resistive magnets, as Omkar was alluding to in a few slides in the past, and these operate at very low Tesla values. And so while the primary advantage of these systems is not necessarily energy conservation, the absence of a need for a superconducting magnet, which of course requires constant cooling, really constitutes an inherent reduction in the energy consumption, because essentially we can just unplug these systems when they're not being used. Next slide. And so switching back to conventional MRI. So how is a liquid helium kept cold in an MRI scanner? And so essentially to maintain the liquid helium, there's this huge insulation layer around the helium. And that's what's kind of showed in that circular cross section there from the diagram. And there's really a 3-stage refrigeration process. It utilizes a cold head, a compressor, and a chiller. And really these are used together to be able to remove heat from the MRI scanners through thermal conductivity. And so the cold head and the helium compressor transfer heat from the MRI to the glycol in the chiller. So usually the fluid that's actually doing the cooling is kind of a mixture of water and glycol. And then the chiller essentially transfers that heat from the glycol to the outside air. So this is kind of many different hardware components. Sometimes they're slightly different in terms of how they're integrated in these systems, but this is largely the refrigeration process that's used. And of course, all of these components require a significant amount of energy to operate. Next slide. And so the gradient and RF coils also, of course, require a significant amount of power. And so shown on the left-hand side there is essentially just a photograph that I took of the the gradient and RF cabinets from one of our MRI scanners at UC Davis. And so on the left-hand side there, you can see there's 3 different gradient amplifiers. Those are used for the X, the Y, and the Z location. And as I alluded to before, that allows for essentially spatial encoding. So we're able to tune the magnetic field to a specific magnitude depending upon where we are in the patient. And then on the right-hand side is essentially the RF. So that's used for both transmitting and receiving those RF signals. And so these hardware components, when we're not actively scanning, they can actually be put into reduced power levels. And we'll kind of show those in some of the low profiles in some subsequent slides. Next. And so some vendors have also implemented what's called a power save mode. Essentially what they've done is they've already had these kind of hardware components. So they've already had a means of measuring the temperature essentially in the cold head compressor or the refrigeration process. And what they found is when these systems are actually turned off, you can really cycle the operation of those cold head compressors. And so we can see from this load profile where the y-axis is power and the x-axis is time, we can see that after that specific patient exam, the user essentially shut that system off. And after some predefined amount of time, essentially the system goes in that power save mode, where you can see kind of the bottom of that drop is essentially when the cold head compressor is in a reduced state or reduced power consumption level. And so this results in really significant savings. And Jacqueline will kind of detail more of those specifics about that in subsequent slides. Next slide. And so the RF and gradient coil, so all that hardware component that I showed those photographs of before, those systems, as I was alluded to before, those can actually be put into what we call idle mode. And so you can see on the low profile on that left-hand side there, where after the system, utilizes a scan mode, it gets into prepared to scan mode. And then after some predefined amount of time, it'll drop into this, what we call idle mode. Next slide. Additionally, these systems can be put into low power mode. And so essentially what that is the heat exchanger cabinets. These heat exchanger cabinets are not only used for cooling the liquid helium, but they're also used for dissipating some of the heat generated by ohmic losses, or essentially from the gradient coils heating up when they're operating. And so really depending upon the vendor, the time and the steps that are taken to get into this low power mode change. For one of the vendors, it automatically gets put into the state after a predefined amount of time after the end exam command. So that means on the actual console, when a technologist is scanning a patient, they actually have to click end exam, and then there's a predefined amount of time until the system goes into low power. And so next slide. Okay, so essentially what we found at UC Davis is we noticed kind of some specifics about the characteristics of some of our MRI scanners that are quite interesting. We're able to save a significant amount of energy just trying to understand what these energy profiles are like. And so shown on the left-hand side, there's a low profile measured on a 3T MRI scanner at UC Davis. And so what we essentially noticed through metering the system is that during the evening, sometimes the system would go into low power mode. So that's indicated by kind of that green shaded region there, and sometimes it wouldn't. And so these are essentially a day's worth of scanning and then the nighttime, and then another day's worth of scanning and then the nighttime. And so essentially what our technologists did is they would, after the last patient scanned for the day, they would restart the system. For reasons I'm not going to get into, we didn't actually fully shut these systems down. But essentially what we found that is that if the technologist did not wait 15 minutes before restarting the system, essentially that timer that says put the system into low power mode, that would completely turn off. And so they would reboot the system before that 15 minutes after the end exam, and essentially the system would never go into low power mode. And so this was really an easy fix for us. Essentially what we did is we told the technologist to, instead of in the evening after the last patient restart the system, do it in the morning. And we found that this resulted in significant savings. Is the next slide. So we really call this a data-driven operational change. Without the data, we would not have been able to change the operation of a specific system. And so that vertical kind of dashed orange line is essentially showing the time at which we instructed the technologist through the lead technologist. So we communicated with them and they communicated with all the technologists. We're able to basically simply restart the system in the morning. And now every night that system goes into low power mode. We see a 10% reduction roughly over the year. And if we have projected annual savings, that's about 3,000 kilowatt hours or 2.9 metric tons of carbon dioxide equivalent. So, this might not seem like a huge amount necessarily, but this is just one scanner at one institution. We have about 16 systems. So not all of them are going to be able to see savings like this, but you can imagine the savings if this were to be extrapolated across the board. And so this is really a simple solution. It came from metering. All we had to do was instruct the technologist to restart the system in the morning, and we see significant savings. And again, without measuring the energy consumption of the system, we could never have been able to figure out this unique characteristic. Next slide. So, modern MRI systems have deep learning reconstruction. And essentially what this allows for us to do is it allows for us to be able to get accelerated pulse sequences. And accelerated essentially means shorter time period. So we can have shorter time period of some of these pulse sequences and be able to use deep learning reconstruction to really preserve the image quality. So all major vendors have deep learning reconstruction for accelerated pulse sequences. On the right-hand side, there is some measured data from 2 of our MRI scanners at UC Davis. And, you know, as expected, as we decrease the acquisition time, so on the x-axis, as we go from the right to the left, we can see a significant reduction in energy consumption, of course, because energy scales linearly with acquisition time. And so this has many co-benefits. Of course, we're getting reduced energy consumption. We're getting shorter scan time. This can also, not necessarily until you change the actual scheduling period, but this can improve patient throughput. If the scans are shorter, you can have more patients scan throughout a day. And this could be advantageous, for example, for growing hospitals. You know, instead of maybe buying an extra MRI scanner, you can actually shorten the scheduling time and be able to have higher patient throughput. So maybe not purchase that next MRI scanner because you're able to scan more patients by better utilization of your equipment. And then, of course, for the patient, this is also more comfortable. They're on the scanner less amount of time, and that also results in less patient motion. So, you know, a lot of the times we get pretty substantial motion artifacts, especially for some of these long acquisitions. And so reducing that scan time really reduces the motion artifacts that can really obscure visualization of specific indications. Next slide. Okay, and so another thing that we're looking at UC Davis is we want to be able to quantify of course, the energy consumption of our MRI equipment, but for many cases it can be kind of difficult to do this. And so what we wanted to do is essentially look at load duration curves. And so load duration curve is a graphical representation showing the relationship between the magnitude of a load and the duration of time that load is sustained. So you can see on the graph here, we have power on the y-axis and cumulative time on the x-axis. And so here the data is arranged in descending order of magnitude instead of a time-dependent plot, as I was showing before for load profiles. And so load duration curves, or LDCs, are really fundamental tools that are used across various fields to analyze and understand the behavior of systems. And we really feel that these could be useful for analyzing the energy consumption of MRI scanners. And so particularly they can be used for classifying different system modes. And accurately classifying system modes for MRI scanners can really enable healthcare organizations to identify potential opportunities for energy savings. And using traditional methods, for example, like scanner log files, it's really technically challenging and cumbersome. Every vendor, every model has its own kind of format, if you will, for these scanner log files. Many times they're at millisecond temporal resolution. So for a single exam, you have thousands of data entries. And so this is really technically challenging. And so it really puts classification of system modes out of reach for many healthcare facilities. Next slide. And so essentially what we did is we tried to develop what we call a semi-automatic analytical method that really does not require scanner log files. So for the sake of time, we can't really go into the details on how exactly we do this, but please refer to our paper. Happy to answer any questions about that. And so essentially what this allows for us to do is to be able to essentially segment the load duration curve and then be able to estimate the time, power, and energy of the different scan modes for our specific systems, again, without the need for scanner log files. So for example, shown here, we see for this, the M1 scanner, for a 1 day period, we see about 25% of the time it's in scan mode, 30% of the time it's in prepared to scan, about 5% in idle, and about 40% in low power and off mode. And so, you know, you can imagine that there's many different applications of this, because essentially you just take the energy data and you're able to generate these load duration curves and then semi-automatically segment them to be able to predict these different system modes. And so next slide. And so this is an example of what we might be able to do with that. So what you can see here is on the y-axis is total energy for weekdays only. And the blue bars are for the daytime, for 7 a.m. to 7 p.m. And the nighttime are shown in yellow bars. And again, this is for one specific scanner. And so you can see that most daytime energy consumption occurs during prepared to scan and scan modes, as expected, given that most patients are actually scanned during these times. And so, of course, daytime energy use really correlates with demand on the grid during times of variable generation, particularly in areas like California, where we have a high penetration of renewables. And so understanding when and in what mode MRI scanners consume energy can allow for optimization of scanner schedules and operations, hopefully to minimize energy consumption. Next slide. And so there's many ongoing projects at UC Davis. We've successfully installed some permanent metering, and we're working on comprehensive metering. So not only metering the main power distribution unit for these systems, but as Omkar has alluded to before, also metering the chilled water supply, if applicable, and also looking at the energy consumption of the HVAC systems in all of these imaging suites. Also, we want to look at scanners specific operational changes, kind of some of the examples I was showing in the previous slides. We want to develop energy efficient protocol optimization. So some of the work of medical physicists is for protocol optimization. So we want to put some of this in the lens of energy savings, and of course disseminate findings so that other universities can utilize this work. Continue collaboration with other medical centers, and probably most importantly, continue collaborations with vendors, as they're really the driving forces because they develop the software and hardware solutions for some of these energy savings. Thank you.
Awesome. All right. Well, next I'm kind of just gonna wrap everything up. If you guys have any questions, feel free to be thinking about them and asking them in the chat. So I'm really thankful to be on this panel and talking with everyone. The research that we have done with UCSF and with ASHRAE, we really needed the help of multiple groups and entities to see how everyone was collecting data, how their method of testing was going. So just this presentation alone really just shows that how much we've been talking and working with others to make this research go even farther. So our method of testing, we felt it was really important to create a standardized method of testing. As Gail mentioned earlier, this research is being used by multiple entities. So we first started off with working with UCSF on the MRI study, and then we started working on the ASHRAE study for the heat gain of large medical imaging equipment. And at the same time, we were also in discussions with the EPA and DOE as they were going through their own study for Energy Star specification of medical imaging equipment. And again, it's just very important that we all share our data and continue on for the next steps. So what I'm going to go through next is kind of our process for doing this study, and to show that, you know, it can be done by others, it can be done by other hospitals, and having a meeting later this week to talk with a researcher wanting to look into mammograms with UCSF. So yeah, we're continuously going to the next thing. So that's what's great about all of this. So how we created our method of testing, we started off with the UCSF procedure, and then looked at the European COSIR procedure and the ASHRAE RP 1343 procedure, and then finished with the Energy Star method of testing. We did have Omkar and his team at NRail did a peer review of our method of testing, and eventually this method of testing will be published under the ASHRAE Medical Imaging Equipment Energy and Heat Gain Study. Each meter is installed by a licensed electrician. Omkar talked about that previously, of who's all involved in these metering capabilities. For Mazzetti, we're fortunate to have electrician on staff, Jeff Rodriguez, who he installed the meters at UCSF and our other hospital partners along the West Coast. We do have a hospital partner in the Midwest who decided to use their own electricians to install the meters, and we were able to work with them over the phone on how to collect the data, and they sent it to us so we could do the data analysis. So in each case, it's very important to talk with facilities on how these meters should be installed, and work through what their processes are. The meters that were installed for UCSF and our other hospital partners were temporary meters. They were installed in the MRI equipment room on the main disconnect panel. We also have other medical imaging equipment that we have are metering as well. Sometimes there are control rooms or equipment rooms where this main disconnect is located. Other times we are connecting at the panel itself. So really, it kind of dependent on what equipment you're looking at. But the picture that you see here, this is one of our installations. You can see the meters sitting in the panel. We would install those and then close the panel after after we're installed, meters would be collecting for 2-week period of time, 1-second intervals, and then we'd come back and our electrician would remove the meters at that point. One of the nice things about having the temporary meters is that we could install these when the equipment was still in use, so we didn't have to turn off the equipment or anything. Again, it's up to the facility on how they would like to pursue this. We have other hospital partners that want to do an official lockout tagout procedure. And so we are working with them to install those meters at that time. So next I'm going to talk about calibration tests that we conducted on our MRI models and also on our other medical imaging equipment. But this was the baseline for all of our models. So calibration test, we decided it was very important to have some sort of test be our baseline across all of the different manufacturer models, because one of the issues that was brought to our attention is that it's very difficult to compare energy when you have, especially in in-field testing, when you have different sizes of patients, different scans that are done. And so we wanted to see if there was a difference for one and how we can have a baseline again. So we use an ACR Phantom of 100 pounds for MRIs. This is pretty standard across all hospitals to have a Phantom like this and to calibrate their machines. We worked with UCSF radiology technologists to create the standardized tests that you see here and that we're showing in our method of testing. For other medical imaging equipment, we ask our technologists to indicate what calibration tests they are using. So again, we can look at when they are doing this test. And because of this, we don't have to look at patient data, and we don't have to look at what times and specific scans were done and to get into HIPAA laws. So I think this was really alleviated any issues with our different hospital partners by having this calibration test. Oh, and I just realized I wasn't clicking to the next slide, so sorry about that. But here's the Phantom that you can see here. It's 100 pounds. And yeah, again, this is just very standard for hospitals to use and for MRIs. Okay, next I'm going to talk about just kind of our data analysis that we did. So here is a 24-hour period. Andrew was talking about this earlier, so you guys have already kind of seen these graphs. But again, we collected time or data over a 2-week period of time, 1-second intervals. So you can see here, this is what a patient exam looks like as far as the spikes go here. We worked with Bruce Norman from Lawrence Berkeley National Laboratory, who helped us with the data analysis. He has a background in electronics for creating Energy Star testing and research for printers for over 20 years. And he was helpful in reviewing, compiling the data. So how we are doing the data analysis is very typical and standard for electronics. Okay, next, Andrew talked about this earlier about a load duration curve. We did the same thing in our study of this is how we created, we saw what the different modes were. We created a load duration curve for each equipment. We did convert data from the 1 second to 1 minute intervals as we were looking at the consumption, and the 1 minute was sufficient for our data analysis. Data is organized from least to greatest kilowatts, and then again, using this low duration curve, we're able to look at what those different low power mode, idle mode, ready to scan, and scan mode based on the graph that you see here. Next, this is our calibration test for one of our MRIs. So again, we asked our technologists to indicate on our sheets that we send to and leave at each site of the start and stop time of that calibration test, so we can see what the maximum energy was used, and then also look at the average energy during that scan. And then next, here is our table that we use for each equipment. We again look at the power modes, understanding what the average power mode is for each of those modes, the percentage of time, and then percentage of energy. This is all of the MRIs that we had studied under the UCSF MRI study. So this is 18 MRIs, comparison of the 3T MRIs that are in green and the 1.5T MRIs that are in orange. In all cases, the MRIs were operating in the low powered idle mode 50% or more of the time of the operation of the equipment. So zooming in there, we can see that there is quite a wide variety of, in those low power and idle modes, the kilowatts being used. Some of the really low power that you see here, that is that power save mode that we kind of talked about earlier, that Andrew mentioned. But yeah, the different operations of how this equipment is going definitely affects what your overall energy use is. So that's where we come and start talking about what is the operational savings. So we talked about earlier being able to change those equipment and the usage of your equipment, how to make sure that your equipment is actually going into a lower power mode. And then we're also looking at pieces of equipment that have power save modes. So UCSF Radiology Department, at the same time, we were helping out UCSF with the MRI study. They were conducting a research with Siemens, looking at 4 different MRIs with 3 different manufacturers, all 3T MRIs. And they collected over a 1-month period. And from their findings, they were looking at what would happen if you were to put all of your equipment operating it in that idle to off mode, and then also to look at what would happen if we were to have a power save mode on that equipment. So just looking at a single MRI, going from idle to off, we could have a 16.65 megawatt hours annual of energy savings, which results in 2,330 annual energy cost. And then the power save mode, additional 10.1 megawatt hours annually and 1,410 annual energy cost. And if we look at that across all of the 24 MRIs that UCSF has, that's a total annual savings of 682.8 megawatt hours and $87,600 annual savings. So creating operational strategies for outpatient radiology departments to utilize turning equipment off in the evenings. We say off, they're not totally off. But in those lower power modes and during non-clinical hours can save a lot of energy costs for existing equipment. And then also, like we mentioned before, manufacturers play a huge role in this too, of creating new ideas and new ways that they are continually saving energy when they can. I think there's a lot of great possibility for energy savings for large medical imaging equipment that is on the horizon.
Great, thank you all for your presentations today. We do have a few questions that have come in. I want to make sure we save some time to get to those. So first, we have a question that says, you mentioned a pre-scan mode for the MRI and the fact that timing for patients can be critical. How long does it take the MRI to move from low energy mode to complete the pre-scan process? And how does that affect timely patient care? I think that's for you, Andrew.
Yeah, I don't think there's really a one size fits all, unfortunately. I'd love to come back and say this amount of time and this fits into that timing paradigm, but unfortunately all scanners are very different. I'm not quite sure what the question was pertaining to pre-scan. Maybe some of the in the idle mode for the operational system modes, we define the warming up of gradient RF coils as maybe that's what they're alluding to. Unfortunately, it's not really something that we can control as users, but it's definitely something that needs to be considered For example, if we're trying to turn these systems off or putting them into low power mode, the time it takes for them to get back into a state where we can really instantaneously scan is very important. And again, unfortunately, it's not one size fits all, and there isn't enough data yet to really predict that well.
All right, here's another question. This is for both Gail and Andrew. Are you working or communicating with other UC campus radiology departments? Or if I present this concept for a new project, will they be unaware?
So there is a UC system-wide radiology group that has been meeting on a regular basis, and I'm not quite sure how often, but there is discussion to share information across all of the 5 UC health systems. So I'm hoping that that will come up, and it hasn't. We can reach out to Sean Woolen, who you see on the acknowledgement. He's been the primary person focusing on that. So sean.woolen@ucsf.edu would be his contact email, and you can reach out to him.
Yeah, and so we are going to begin actually working with Sean and Alistair a little bit more, kind of sharing data. You know, because we have different scanner fleets, I think it's really important to be able to you know, collect that data and comprehensively look at it, because again, every vendor and every model is different, and so it'd be good to get a large picture of that. And so I think that's really important. We are working with UCSF. I work with other UCs on different projects, and I just presented at a physics, medical physics meeting where we shared that with multiple universities. I know UC Irvine is relatively aware. UCLA is, but maybe not so much San Diego. I haven't necessarily specifically spoken with anyone there, but I would imagine that that some of them are aware of some of the work that's happening. But whoever, I think that was an anonymous question, but feel free to contact me or Gail. Happy to chat or you know, communicate and collaborate to whatever extent necessary to hopefully you know, start bending the climate curve here.
All right, we have another question for you, Andrew. Would the low power mode and other measures that you mentioned to reduce energy consumption of MRIs while not in use be applicable to MRIs in general? Or are those capabilities vendor or model specific? I'm trying to understand if these recommendations are operational with existing equipment or performance characteristics to look for when we're replacing our equipment.
Yeah, absolutely. Great questions. Again, I know I've said the same thing a few times over and over. Unfortunately, every model, every vendor, every software version is different. So even if you have the same model, you could have a different software version that changes some of these characteristics, if you will, of some of these modes. And so I think that that question might have been pertaining to the data-driven operational changes. We have only seen that for one specific scanner make and model. Not necessarily, it's not necessarily true across all. What was that person's name? I can't remember who it was, but feel free to email me and I can give you a bit more specifics. Unfortunately, I didn't feel like this is a good platform to kind of dig into the very specifics of that. But you know, the definition of those system modes is something that we tried to have encompass all vendors. And so that's why it's so long, and that's why there's so many different bullet points, is because every vendor is slightly different. But most of them do have, you know, scan, prepared to scan, idle, low power, and then of course off mode. But the time it takes for them to get in and out of those modes does vary based upon make and model.
All right. Lastly, is there any curriculum being built to teach physicians ordering imaging exams based on environmental impact? For example, if ultrasound can provide similar information, can it be used instead of MRI for a lower energy solution?
I guess I'll take that one as well. So yeah, I mean, I think that's a discussion that can be quite fruitful. I think there's a lot of different universities that are looking at that. You know, what's the value of that particular modality? Many times, for example, for follow-up of specific indications, where conventionally we use MRI, but ultrasound can be used, that'd be a great alternative. And so I think that that's an area where once we are able to really establish baseline understanding of the energy consumption, we could then use that to really model different paradigm or different strategies for follow-up that we can employ that are hopefully less energy intensive. And so I think to answer that question concretely, that is an area that people are looking at. And hopefully, that's not the only story, of course. The diagnostic quality of that modality is of utmost importance. But I think if we can use energy consumption as part of that story, I think that will be powerful moving forward.
Great. Well, thank you to each of our panelists and to all of our attendees for the great questions. Please mark your calendars for the next Bending the Climate Curve learning event on September 17th at 8 a.m. Pacific, 11 Eastern, where we will explore the electrification of central utility plants. With that, we will adjourn. Thank you all.
Thank you. Have a good day.
Thank you. Have a good day.